only two things we want to learn today. One is famous Arrhenius equation. So this equation basically summarizes all the relevant parameters that's going to affect your chemical reaction kinetics. Once we finish that, we are going to talk about what does catalyst do, how it actually affects the chemical kinetics. So it's more conceptual things. All the concept that we're going to mention today is really this guy. Scientists actually spend a lot of time to give you this equation. K is the rate constant, right? So larger the K, process move forward faster. Rate constant is actually related to two terms. You have these A terms, and then you have this exponential terms. The A terms is so-called the frequency factor. It describes two things. For a reaction to occur, the reactor need to collide with each other. So the collision frequency, it contains the information about how frequent the reactant actually collide with each other. When these two things, they are colliding with each other, in order to make the reaction to eventually occur, these two things actually collide in the proper orientation, Z. So these two things need to satisfy simultaneously so that the reaction can occur. The terms that you have this E, negative EA over RT. Okay, so this term is so-called the exponential term. There are actually two important parameters inside this exponential term, right? One is EA, one is T. EA is the activation energy, and the T is the temperature. To understand this, we're just going to start with an example. So we use these reactions. CH3N3 is going to isomerize into CH3CN. Structure-wise, it looks like this. Okay, that's your reactant. And your product is this. Okay, so it's kind of like just changing the orientation of this. When scientists actually start this reaction, they believe these reactions go through a transition state like this. Then you have this very special symbol. They believe the reaction should actually go through this and then go to here. So every time you see something labeled with this is something called the transition state. Whenever you call a species is in the transition state, it is not isolatable. Means actually when you do the experiment, you can actually really isolate this species. We just propose there's actually something exists very transiently. So we are going to use this as an example to explain this diagram. Okay, so this diagram is actually a very important diagram. You need to actually know how to draw this diagram yourself. You need to know first, know the X and Y axis. Okay, what is your X axis? Time, right? So like you start from the reactant and you end up with the product. It's describe the progression of the reactions. Sometimes you will see things actually labeled differently. Sometimes they will just say this is actually a reaction axis. But it means the same thing. It means actually the reaction goes from your reactant to the product. So let's say your X-axis. What is your Y-axis? Energy of the species. It's not the energy of the overall reaction. It's actually energy of the species. You start from your reactant, you end with your product. This represents the energy of your reactant. This represents the energy of your product. Go from your reactant and end up with your product. You just have a one line connected with that. So once you do this, you can first calculate the energy of your reaction, which is your delta H of reaction, right? It's actually the enthalpy of your reaction. How do we calculate this? It's actually the enthalpy of your product minus the enthalpy of your reactant. Figure-wise, it's just extend your energy line of your reactant. Okay, then you know the energy difference between your reactant and the product that give you your delta H of reaction. The other thing is, you see this, you need to actually get over a certain energy so the reaction can occur, right? So the highest energy point of this curve was defined as the transition state. So the energy difference between the highest energy of your transition state and your reactant was defined as the activation energy. This is a Endo or exothermic reaction? This is exothermic, right? How about the endothermic reaction? Let's draw these things out. That is your reactant. That is your product. That is the endothermic reaction, right? The delta H will be, this is your delta H reaction, right? That will be your EA. We are going to extend this concept a little bit more. Again, start from your reactant and with your product. If you see a curve like this, do you know how to calculate your delta H? It's still the same, right? The energy differences between your reactant and product. This is your delta H of reaction. Where is your activation energy? The highest point, okay, so it's here to here. That is actually your EA. So what is this? So in this reaction, how many transition states you have? 3 transition states you have. The question I'm going to ask now is actually new. What are these? Energy-wise, they're actually at the local minimum. That means they can be isolatable. So this is so-called the intermediate. Okay, so how many intermediates in this case? 2. So these are the type of questions you're going to ask in your homework. That's pretty much all you need to know for this plot. All right, so let's talk a little bit more about this equation. So let's talk about the exponential factor term first. On the top is activation energy. At the bottom is actually temperature. Let's look at how temperature is going to affect these terms. Assuming our temperature is infinity high, EA over RT is going to approach to 0, right? So we know your exponential term will become something like this. It's going to roughly equals to 1. The second extreme, if your temperature approach to 0, then your EA over RT is going to approach to infinity. Therefore, you know your exponential term will be exponential to the negative infinity. This is going to give you a number of 0, right? So you know at the high temperature, your exponential term give you 1. At very low temperature, your exponential term give you 0. It means your exponential term always between 0 and 1. It's because that this term is going to describe how many molecules has energy that's actually above activation energy. This term is going to tell you how many of the molecules, okay, in your system has energy higher than your activation energy. Because only those molecules can actually go to your product. That's why it is between 0 and 1. Tell you what is the percentage of molecule can eventually lead to the product. So every time when you turn up the temperature of your reaction, what you really do is just create more high energy molecules that can jump over the active energy barrier that give you the product. So let's actually one more thing that you want to think about it, which is actually the unimolecular reaction. When you have unimolecular reactions, typically it's actually a decomposition reaction. In that case, your A, since you're not going to collide with each other, right? You just dissociate yourself. So the collision frequency is not important in this case. The proper orientation is going to be replaced by the proper vibrational mode. Then the A in that case is going to describe is that it's in the right proper vibration mode that will lead to the product. But for the bimolecular reactions, A is going to relate it to your P and Z, right? Where Z is actually the collision frequency, and your P is actually the orientation factors. Experimentally, so how do you determine your K and the EA? Okay, so those are the 2 things scientists always look for. And typical measurements we are going to do is actually you measure your reaction rate constant as a function of temperature. If you look at these equations, to remove the exponential, scientists actually take the natural log on both sides. So you have natural log K on the left. Sorry, this should be actually lowercase k. On the right will be this first term become natural log A, right? The second term, all you have is actually negative EA over RT. So I'm going to rewrite this. It becomes natural log K is going to equals to natural log A minus EA over R times 1 over T. And the reason I do this is because I want to let you know, okay, if I make this as my Y, this is my X. Then I can write this as Y equals to C minus AX. And this is actually a linear equation. In other words, if I plot out my natural log k, x is actually 1 over t, then I should expect to see a linear relationship. The slope is going to equals to your negative EA over R. Intercept should give you natural log A. For scientists, they measure the K at different temperature. Once they have this table, what I do next is actually they convert it into 1 over T. On the y-axis become natural log K. They're going to plot the things out. So they can just fit the point to get the slope and then get your natural log A. You know your slope is negative EA over R, right? So you can actually back calculate what is your EA. You can actually get the A using these numbers. If I really do these things, I plot these things out, and I do the fitting, then you can get slope equals to this, and then your intercept is going to equals to 31.4. Starting from here will be something you're going to see in your homework. What I'm going to tell you is actually, okay, a scientist is doing an experiment. They measure this rate constant at different temperature. When they plot out their natural log of K versus 1 over T, they see a straight line. And then when they fit that straight line, they realize the slope is this value. The intercept is that value. And it's going to ask you, tell me what is the EA of the reaction? What is A of the reaction? Because we know the slope, okay, is going to equal to negative EA over R. R, in this case, you need to always use 8.314 joules per mole. This is actually different from the things we told you in the chapter 10, where you need to use the gas constant for that. Okay, but here it's actually 8.314. So slope from the question you know is negative 19400 equals to negative EA is actually the things we want to solve for. R is 8.314. So if you do this calculation, you'll realize your EA is going to equals to 161,000 joules per mole. How about your A? A comes from your intercept. Intercept is going to equals to your natural log A is going to equals to 31.4. Take exponential on both sides, then you get your A is going to equals to exponential 31.4. And then give you a number of 3.92 times 10 to the 13 per second. This reaction is just a isomerase process, so it doesn't have the collision terms. So here the A is telling you how fast this molecule is actually vibrates. They can actually reach the proper orientation that lead to the product formation. And if you look at this number, it's actually quite crazy. 3.92 times 10 to the 13 per second. That means within a second, your molecule vibrates that many times to sample the proper configuration that can lead to the product formation. Another type of question you're going to see a lot in your homework is something like this. Typically in these questions, you're going to see two different temperatures. So the keyword for this type of question is actually you see two temperatures. So how does this work? Previously we say the reaction rate constant K, again, this should be actually lowercase k. Natural log K is equal to natural log A minus EA over RT. You can do the experiment at different temperature. So in this case, you can do the temperature at T1, which you can write out your natural log K1 is equal to natural log A minus EA over RT1. You can do your temperature at T2, then you can write out your natural log K2. It's going to equal to natural log K minus EA over RT2. Use equation 1 minus equation 2. Therefore, on the left, you have natural log K1 minus natural log K2. On the right, you have natural log A minus EA over RT1 minus natural log A minus EA over RT2. In this case, natural log A is going to cancel out. So if you summarize things, then you're going to see this natural log K1 minus natural log K2 equals to EA over RT2 minus EA over RT1. Then you just combine this. When you do the subtractions, we blend together, it becomes division, right? This one, you just pull out your EA over R outside the parentheses. and inside will be 1 over T2 minus 1 over T1. So if you look at this equation more carefully, there are 5 parameters: K1, T1, K2, T2, and EA, right? So the question you're going to encounter is actually a question that's going to give you 4 of these parameters and ask you to solve the 5th one. For example, it can give you K1, T1, K2, T2, ask you for the EA. That's one type, right? The other one is actually if I give you T1, K2, T2, EA, I can ask for the K1. So let's give you one example. The rate constant of a first order reaction is certain number at certain temperature. What is the rate constant at different temperature if the activation energy is certain number? So here the things you should quickly see is apparently there are 2 different temperatures, right? Therefore, you know the equation you should use, natural log K1 over K2 is going to equals to EA over R 1 over T2 minus 1 over T1. Don't mess up the order. Okay, otherwise you will never get the proper answer. This is actually the part I see students make mistake. You say if you want to do this, then it will be 1 over T1 minus 1 over T2. So I'm going to list out T1 equals to 98, right? Which I know my K1 is equals to 3.46 times 10 to the negative 2 per second. T2 I know is actually 350 K. Okay, K2 is the things I want to solve. EA is going to equals to 50.2 kilojoules per mole. So this is another part that many students will make mistake. When you put in your EA, it has to have the unit of joule, not kilojoule. So to convert this one is actually 50.2 times 10 to the third joules per mole, right? And that's going to equals to 50200 joules per mole. And then we know our R is 8.314 joules per mole, right? You will solve for your K2 properly. I will just give you the number here. The K2 is 70.18 times 10 to the negative 2 per second. Okay, so the key thing about the catalyst that you need to know is that catalyst is the substance that's going to speed up your reaction. The catalyst will never be consumed, and it will never appear on either side of your chemical reaction. So when we write a chemical equation, we know the things on the left side is the reactant. On the right side is your product. The catalyst will never show on either side. The only place the catalyst will show up is above this arrow. So what does the catalyst do? It's actually related to the activation energy. This is actually the type of curve, okay, when you have catalyst versus without catalyst, how it should look like. That's your reactant, that's your product. So this actually is your delta H, right? Okay, and this is actually an endothermic reaction. That is actually your activation energy. So you can see without the catalyst, you have actually much higher activation energy on this plot. But once you add in the catalyst, what it does is actually it lowers down that much of the energy. Why is it important to lower down your activation energy? It can be explained by this, okay, this plot. So we say this exponential terms contain this EA and the T, right? That means at a given temperature, there's only certain population of the molecule is going to have higher energy than the EA, which can actually give you the reaction product. Assuming that is the energy distribution of your molecule. And then this is actually your activation energy. That means that only this portion of the molecule is capable of produce the product. So right now you add in your catalyst. What it does is actually lower down your activation energy. On the plot, what it means actually it pushes this one back to a lower energy. What's going to happen is that now you have this much extra molecule. They are actually higher in energy than your activation energy, right? Which means actually all these things can actually contribute to your product formation. So that's why the catalyst is powerful. What it does is actually lower down the activation energy. We know the only thing it does is actually change or lower your activation energy, right? So that's the things it does. The things it does not change is actually to your equilibrium. So remember this chapter is talking about what? Talking about kinetics, right? It's actually talking about how fast the reaction can occur. The catalyst is going to lower down the activation energy. That means actually the conversion from your reactant to product. This process will be speed up. But it did not actually affect the final equilibrium constant K. So this is actually a very, very important concept because in your homework, they will ask you, what are the belongings that the catalyst will change? I guarantee you, they will say the equilibrium is one of them in the question. That is not the answer you should select. The only thing you should select that the catalyst can change is activation energy. Okay, it's going to lower down your activation energy. That's the only answer you should select, nothing else.